Carlos Cardona from University of Arizona in the States. He got his PhD from University of Buenos Aires, Argentina, and then he moved to a research position in Sao Paulo, Brazil, and then to the National Taiwan University, and finally in the Niels Bohr Institute before his current position. So, Carlos, you have 40 minutes for your talk, plus 5 minutes for questions. So please go ahead.
All right, thanks, Brian, for the introduction. And thanks to all our organizers, Lorenzo in particular, for giving me the opportunity to talk about some of my work. Right, it would be nice to meet in person, but I guess we still are in the virtual setting. Hopefully, this is gonna end soon. Right, so I didn't agree with Matt or Andres or the other speakers that give a kind of overview, but I also decided to give a kind of an overview. Mine is going to be less general than the one done by Matt. I'm just going to touch on some topics that I've been working on for the last 3, maybe 4 years. I'll give an overview of those corners that I have touched. Yeah, so in summary, I'm going to discuss some analytical approach for the bootstrap program in dimension greater than 3. Then I will show how those results can be obtained in an easier way from even newer methods. And then I will show also how some numerical methods can be applied to this conformal bootstrap problem. And then I'm going to go down in dimension to 2-dimension and discuss some challenges that are still present in 2-dimensional case and end up my talk. So here we're going to, okay, so what is the conformal bootstrap? The conformal bootstrap is the intersection or the union of 2 very old ideas, not very old, but fairly old ideas, not new, which one of them is the bootstrap itself. So the bootstrap was an idea first applied to quantum field theory in the 60s within the, analytic S-matrix program. I would disagree with Matt. Unfortunately, he's sleeping now, but I would disagree with Matt in regards that the S-matrix analytic program was unsuccessful. I would say the S-matrix bootstrap was very successful, not as successful as perturbative QCD, but it was very successful because it led us to many things that otherwise would not be realized, like, for example, Regge theory, and, what is the name of this? Well, anyway, a lot of stuff that were obtained later by using Regge theory. The Froissart bounds, those were computed within the bootstrap in QFT. String theory was discovered by bootstrap techniques, by the way, from Veneziano, trying to find a formula that obeys crossing symmetry. So it was not a complete fail. So we are going to put that idea together with some other old idea, probably older than the bootstrap, and is the idea that we should be able to classify quantum field theories in families. There are universal behaviors that classify, quantum field theories within families. In particular, we're worried about the universal classification of critical phenomena, for example. So, we know that, like, for example, the Ising model, which is the most popular critical system, belongs to the same universality class of the very unrelated and very different theories. Like in 3D, the 3D Ising model lives in the same university class as the boiling of water. So there are two very different phenomena that they are related because some observables are the same in the sense that they have the same numerical values. In this case, the critical exponents has the same numerical value. So that's kind of a mystery in many situations. And we are going to try to use the bootstrap to try to tackle this classification. So we put these two ideas together and we have the conformal bootstrap. Let me introduce some notation. In conformal field theories, the quantum numbers that we use to identify operators are the conformal dimension and the spin. I'm gonna interchangeably, I'm gonna be using both the twist, which is defined by this subtraction, and the conformal spin, which is defined by this addition. So when I say tau or beta, you can as well think as delta and j, spin and conformal dimension. And also I'm going to constrain myself to 4-point functions of scalars, and even more I'm going to consider the simplest thing, which is that the scalars, I have 4 scalars in the 4-point function and they have the same dimension. So essentially they are the same guy, 4 times. Conformal symmetry, so the first constraint that conformal symmetry imposes, or perhaps one of the most powerful, is that a 4-point correlator, for example, can only depend up to this global factor, can only depend on cross radius. So can only depend on z bar coordinates, and they're defined by this radius. These expressions here, you can think of, so this is an scattering amplitude community mostly here. So you can think of c and z bar as the Mondes and invariants in a theory which is Lorentz invariant only, not conformal invariant. So that's some notation there. Right. So the other constraint we're going to impose, following the bootstrap philosophy, is crossing symmetry. I have make pictorial representation of what crossing symmetry means. And in reality, that's what it means. I'm just interchanging 2 external operators, 1 and 3. And that, since I only have the same scalar in the 4-point function, interchanging 2 of them should not change the value of my observable. So that's what I am imposing here. The other imposition we impose, the other constraint we impose is that there is an OPE expansion. So we assume that there is a way that the multiplying 2 operators in my theory could be written in terms of a sum of a linear combination of single operators. Anyway, so there is this is a consequence of the existence of an OPE expansion for operators. And then unitarity will constrain these coefficients in this expansion by imposing those coefficients to be positive. And also it could constrain the dimension by saying that, well, the dimension and the spin, or this combination, which we call the twist, to be greater than the space-time dimension -2. So these are 2 constraints coming from unitarity. Once we have all these constraints in place, when we want to see how much information we can recover from that. So one classic analytical approach. So now I'm going to start talking about the analytical approaches. One classic analytical approach, which started in 2013, perhaps, from the authors Archiboedo, Komardowski, Fitzpatrick, Kaplan, Maldacen, Aldai, and many other people. And the approach is very simple. You say, well, let's go to the Lycon. So if you look at the cross radius, going to the Lycon means making these distances null, right? Making these distances on, the positions of this part, the position of the operators in my correlator to live in the Lycon, on the Lycon, on light rays. That implies to the cross radio that the one of the cross radius goes to 0 and the other goes to 1. You just need to look here. So if these 2 distances become null, the denominator becomes 0. So this means that one of these guys is 0 And these guys also become 0. That means that one of these two guys becomes 1. So if I go to that region, first taking the z 0 limit, we know for a fact that these guys are called the conformal blocks. I'm sorry, I forgot to define those guys. So these guys only depend on conformal symmetry, and the information about your particular theory you are looking at is encoded in these coefficients. This is a purely symmetric, these conformal blocks are just consequence of the symmetry, so they are established. You can compute them only by knowing the conformal symmetry, and they are known as conformal blocks. So we know those functions. Not all the time, I will say when we don't, but for dimension greater than 3, dimension greater than 2, we know those guys. And we know that taking that limit, the Lycon limit, these guys factorize in this particular way. There is a power in Z and then a function that we know in Z bar. And unitarity make another important constraint here that does not happen in 2 dimensions. So in unitarity said that each operator in my spectrum should satisfy this inequality. That means that you see, for the vacuum, I have delta equal to 0 and spin equal to 0. And the next operator, so the vacuum is the vacuum, doesn't satisfy this condition. But for the next operator in the spectrum, I need to satisfy this condition. So if you are in dimension greater than 2, then these guys cannot be 0. That implies that there is a gap. There is a separation between the vacuum operator, when these two guys are 0, and the first operator that can appear in this sum, which is the lowest dimension operator that you can have in your theory. And this gap is very important because that allows this separation. And what happens with the separation is that this term in the exact limit, this term becomes dominant. And now I need to look for a way to recover that single power kind of divergence, because it's going to set this power divergence from this guy, which is a sum. And then now that we have taken the Z going to 0 limit, we want to take the Z bar going to 1. And it turns out that these guys develop locks at that region. I'm sorry. So when Z goes to 1, one of these arguments goes to 0, and then this factorization still applies. So we have this, and then when Z bar goes to, when C is going to 0, this function, this argument goes to 1, and when this argument goes to 1, the conformal blocks become locks. So how do I recover this power expansion from a lock? Well, I cannot have a finite sum because a finite sum will give me a lock, and I don't have locks at this size. So the consequence of this constraint is that I need to sum over an infinite number of operators. So that has already important consequences. Only this very simple exercise has already very strong consequences. It's saying that in any theory, in any conformal field theory with dimension greater than 2, I don't know what I'm putting dimension greater than 3 here, but in dimension greater than 2, you need to have an infinite number of operators in your spectrum, right? Good. So that's something that we recovered by using this bootstrap thing, right? So that's one thing. The second thing is that now how do you recover this thing if you don't know how to do the sum? We don't know how to do the sum because we don't know these coefficients. These coefficients depend on the theory you are considering in particular. So how we can compute this sum or try to compute this sum if we don't know these coefficients here. So we do what we physicists do when we have complicated sums. We try to pin down the leading contribution, the most contributing term here. What is the region of the sum that is contributing the most to this sum, such as I have a power expansion. So that was done for these gentlemen here, and they realized that the sum is going to be dominated when this condition happens. And this condition implies, due to the fact that Z is going to 0, implies that beta has to be large. And once they have pinned down that region, we can just solve this equation for Z. in around that region for these coefficients. And the solution to this coefficient is something that people call generalized free theories, which are essentially conformal field theories that are free. Right. So okay. So now if we keep doing that exercise, I'm not going to do all the details again. If we keep doing that exercise, we realize that if we go to if we keep including contributions, you know, the next contribution in the left-hand side, and we want to, again, look at how to solve this constraint, we will realize that tau, the exponent here should be small. That implies that tau should be some quantity which is related to the classical dimension of the operator semi-correlator plus some small number. And due to the fact that this sum is dominated in the large beta, it's only natural to assume that we can find an expansion of these undetermined coefficients as, you know, as a Taylor expansion in one of a beta being large. So when people start doing that, they start proposing, you know, not proposing, you kind of assume these ansatz, and then you plug it back, and then you start solving these, solving the constraint, the crossing constraints order by order. And by solving in order by order, you end up having algebraic equations for the coefficients in this series, and computing those coefficients give you an estimation of these parameters. That was done for several years, so people came up with, you know, so they look at particular theories, those particular theories impose more constraints, and then they solve in one of a beta for these guys. There was a lot of good progress in that direction. That was called large spin perturbation theory, because beta become large when you have large spin or when you have large dimension. But then some breakthrough, very beautiful. So an important, yeah. So one drawback of that approach of that Taylor expansion of this kind of perturbative approach is that all those series that they were computing were asymptotic. So this only works. These results only works for beta strictly infinity. You know, very large. So that was bad news, but then some more help from the 60s, you know, from the S-matrix program done during the 60s came to the rescue by using some Null formula, which is now Freussard-Grivot formula. Simon Caron-Huot was able to obtain a very beautiful formula that people now known as the inversion formula. So first, let me tell you what is the Freussard-Grivot formula. Usually, so think about, you have a scattering amplitude, and in a scattering amplitude, we can do, so think that this is a scattering amplitude, you know, this is S and this is T, and in a scattering amplitude, some of this form is known as a partial wave expansion. Difference in that case is that these functions in the relativistic case, they are Lagrange polynomials. In general, in higher dimensions, they are Gegenbauer polynomials. Here are just hypergeometric, so that's the only difference. So the idea of Freussard and Grivot was, wait, by knowing the analyticity of this function, by knowing the analyticity of the scattering amplitude, we would be able to invert this equation and solve this constraint, this, you know, the partial weight, any partial weight amplitude, solve it for these coefficients. And they were able to do that at the time. Of course, the Gegenbauer polynomials were very well-known objects. So they were able to do that. So what Simon did here was try to replicate the same exercise. This was in 2017. In 2017, Simon Caron-Huot tried to replicate the same exercise when, instead of having Gegenbauer polynomials in that expansion, you have a slightly more complicated function, which are these conformal blocks. They are just combination of Gauss hypergeometric functions. Anyway, it's a lot more involved, the derivation in the case when you have conformal blocks, but it was done. Let me explain a little bit this formula. This said, if you have a 4-point function, then by computing the double discontinuity, you have a double discontinuity because the cross radius has 2 branch cuts here. So these two guys will develop 2 branch cuts in complex plane. So you have to compute the double, when you cross these 2 branch cuts, that's that whole the discontinuity across them. That's what this thing is computing. And then you have some particular conformal block. This is the same conformal block we did before, just that the indexes are a little shifted. And some measure factor. And this is just some constant that can be easily computed. Then if you are able to compute this double discontinuity, you don't need to know the whole correlator. You just need to know the double discontinuity. Then you will be able to compute the OP coefficients of U30, and you are done. Of course, that's easier to say than say than done. So my friend Carol Sen and I thought, well, so that implies that if we look for some simple cases when we have an expression for this guy, we can use this formula. And those cases were actually the cases when this Lycon limit applied. So we applied the Lycon limit, but inside this integral, and we were able to perform the integral. And now, instead of having this series expansion in 1 beta, we obtained this similarly complicated expression. Is not that complicated. These omegas are a combination of hypergeometrics. And this is a combination of gammas. And the advantage of this formula with respect to the ones doing expansions in 1 beta is that this expression is valid for finite beta. So this is not asymptotic anymore. This is the finite non-perturbative, if you wish. If you consider that a beta, 1 beta as a perturbative, parameter, then this guy is non-perturbative in beta. And indeed, if I take this formula and I do expansions in 1 beta, we recover all the other cases that Aldai and Chibuero and other people were doing using this large spin or large beta analysis. We went a little bit, a step, a little bit. We did a little bit more than that. This expression is valid in 4 dimensions. So when your space-time is in 4 dimensions, but by using some technique, we were able to generalize this to general dimensions greater than 2. As you see, I cannot take d equal 2 here because then everything is messed up. So for d greater than 2, this expression is valid. And so in few words, the way the method we use is to use a representation in Mellin space. This is a Mellin transformation. So what I mean by that is that we want to write the conformal blocks in a Mellin transform space. So we transform these conformal blocks to applying a Mellin transformation, and then now we can write them, in this Mellin space. The advantage of that representation is that this guy is agnostic to the dimension. This guy doesn't care about the dimension where you are at. The dimension is encapsulated in the poles. As you see, this is a contour integral now. The dimension is encapsulated in the poles of this guy. So shifting the dimension is the only thing it's doing is shifting the poles of this guy. So in that sense, it's agnostic. You bring 4 dimensions and you want to go to 5 dimensions, the poles only shift a little, as you can see from here. Right, so this agnosticity in dimension allow us to apply this in general, and that was, and then we applied the inversion formula and we recovered the anomalous dimension for the particular cases when the correlator can be can be constraint to live in the line call. So when the operators in the correlator are null separated. Now, something nice about these two formulas that I'm showing you here is that they are universal. I haven't done any assumption about my theory. We have not done any assumption about the OP coefficients or the spectrum of this theory. We only use the assumption that this correlator can be computable, that the Lycon limit exists. That's the only constraint. So that means that any conformal field theory that has this property, and only that property, will have in the large beta limit has conform, anomalous dimension that will look like that, like this. Yeah, I don't want to comment on what else has been done. There's a lot has been done. I didn't want to go into, because I want to kind of give you guys an idea of what has been done in different areas in this business. But there are a lot of things done since that paper of mine, so maybe 2 years ago or 3 years ago. But now I want to mention a little bit about the numerical side. So the nice thing about the analytic side, as I said, is that it allows us to uncover some universal properties. As I said, you see, these conformal field theories would correspond to universal families. A given conformal field theory corresponds to several critical behaviors of different theories that, when these theories go to the critical point, they look like a conformal field theory, which is the same or very similar to all these families. So this is this universal behavior is a part, it's in a way a capture these universal classes that I was talking about before. Right, so the numerical side as a complement of the analytic side will allow us to see the space of those theories. Like we will, I will show in a moment, like people doing this numerical stuff are able to see like islands where, families of theories live, where these families of theories should live. I believe that's the monolith that Lucia was talking about this morning. Well, in the case they are considering some, they are not considering conformal field theories, but quantum field theories. But it's the approach is similar. So in the numerical case, how we deal with this numerically? So we start again with the crossing symmetric crossing equation, and then we start applying derivatives evaluated in some particular point. At this point can be any point, but this particular chose is because around that point, the numerics behave very well. So in the middle of the causal diamond, this is the middle of the causal diamond, the numerics are very stable. If you go close to the boundaries of the causal diamond, the numerics start getting jittery and unstable. So this is just a nice point. And applying derivatives to this crossing equation, what it means is that you are making a Taylor expansion of this thing. So in other words, if you now consider, so the formal way to solve these constraints with derivatives is that you define a vector whose components, which components are, the derivatives. So these M and N are labeling for the component of the vector, and they are just the number of derivatives. And this capital F is nothing but the crossing, just written in a more symmetric form. That simple exercise, that just taking derivatives and then represent them in a, putting them in a vector representation, turn this problem into a very easy, it's not very easy, but it's like very, convenient way. The crossing equation into a linear programming problem. Now, for those of you that haven't heard about linear programming is not necessarily related to a way of code, to writing programs in a computer. Linear programming is a mathematical algorithm. There are many mathematical algorithms that doesn't have to be computed by a computer. Linear programming is one of them. So linear programming is essentially an algorithm to solve a recipe to solve a particular problem I'm going to say. When I say linear programming, or when somebody tells you linear programming, you should think similarly to Gauss decomposition. When you do Gauss decomposition, if you have a linear system pretty much like this one, and you want to solve it, and you have, you know that the number of constraints is equal to the number of unknowns, then you say, oh, well, now I'm going to do a Gauss decomposition of this. And that's just an algorithm, right? So Gauss decomposition is a particular case of linear programming. You have a very well-defined recipe to do Gauss decomposition by following a very precise algorithm that you can put on a computer and do it faster. Linear programming is an enhancement of that in the following sense. These constraints are underdetermined, meaning there are less constraints than variables. So variables, you have an infinite number of variables, which are these coefficients, but you only have a finite number of constraints, which is how many derivatives you choose to put here. So that means, if you try to solve this by Gauss, you will have infinite number of solutions. But the linear programming itself is something more than that. You have the linear equations, and you have some additional constraints. One of them is that, by unitarity, the variables, the solutions to your linear equation should all be positive. That's one. And the other is that wherever that solution is, it should maximize a function that is known as the cost function. And the cost function in practice for the bootstrap is just picking an operator from your spectrum and maximize the OPE. That means you want to see how far you can go in your OPE region without violating the bootstrap. You want by violating the conditions you are imposing on the bootstrap. So, okay, this is a very simple example just for you to give you an idea what is these people doing numerically. Well, I have done things, I'm working on some things also with that. So what we do is, it's easier to explain with inequality. So I'm just going to consider an example. Instead of having an equal to 0, of course I can make this equal to, anyway, I'm going to have an inequality. So if you have these kind of inequalities, and these guys are positive, means that you are, in this two-dimensional case, you are in this positive quadrant here. And each linear relation defines a line, right? So this line 4x1 minus 1x2 equal to 8 is that one here. I hope everybody can see it. Sorry, less or equal than 8. That's the one here. And then you have all the three other lines like here that give you that. All those constraints imply that you are in this space. So this space, this gray area, is the infinite number of solutions to that system. But now you want the solution that maximize this other function. So it's an easy exercise to just start evaluating this function within this gray region to realize that optimal solution, the max of this function, lives in this tip. So that's what you are doing, just that with a computer. But the algorithm, you can do it by hand if you want, but you're going to take like weeks. So that's why they use computer. So one of the, perhaps the still most famous use of this numerical approach is the one done by, Cheryl Chalk, Miguel Paulos, David Poland, Rich Cobb, Simon Daffin, and Alexander Vicky, when they, they have the bootstrap constraint, and they also they include as an input the spectrum of the 3D Ising model. So they input things that they know from the 3D Ising model, and then they run this simplex algorithm, this algorithm that I was trying to explain here, to maximize. In this case, they were maximizing, I believe, the OP coefficient corresponding to the stress tensor. Don't matter much. This is the operator that is related to the stress tensor, the dimension. Anyway, that doesn't matter much. What is important, and what is like shocked the world of their result, is that even though all the points that, so here they are plotting this delta sigma is the operator's injure correlator. So this is the scalars I was considering before I called delta naught. And this is the operator they are maximizing the OPE, right? And then they found that the purple region here is the region which allow physical theories, but what was surprising is that the Ising model lives in the boundary of that region, and not only in the boundary, it has a kink. So there is something very particular with the Ising model, that make it very special, that it lives there, and that has consequences that I will not have time to mention. But this kind of, I think this is the result that fuel all that bootstrap, numerical bootstrap, in particular because the critical exponents that they were able to get from this analysis are the most precise ones so far. They are I don't know how many, I think it's twice, I don't remember, but they are better than the state-of-the-art Monte Carlo. So that's kind of sick. With a lot less of computational power, So that was, well, I have like 3 minutes. Is that right, Brian?
Yes, that's right.
Yeah, okay. So let me go very quickly to two-dimensional case. So in the two-dimensional case, in theory, a lot more is known. And the two-dimensional case is more rich, because the main reason is because in 2 dimensions, the conformal symmetry get enhanced. So the algebra of the conformal group in 2 dimensions is infinite. So you have an infinite number of constraints already. Let me put it another way. And you have an infinite symmetry. That is a lot of constraints. In addition, there are some important objects that appear that we don't have in higher dimensions. Well, we do have it again. In 2 dimensions, we have null vectors. We have operators in the spectrum of conformal field theories that have null norm, and they have anyway. So they are not like that null, and they have important consequences. When you impose unitarity and you assume the existence of these operators, not assume, you believe that these operators can exist. You don't want to throw them away, but you want to keep them. So if you keep those operators and also want to keep unitarity, then that constrains your spectrum. So for central charges, now I am introducing notation, term that probably nobody has heard, that no all have heard, but anyway, central charge is this quantity here. So for central charge between 0 and 1, your spectrum can only take some particular rational values, and your central charge can only take some particular values. And what is more important is that when this happens, the spectrum truncates. So these infinite sums that we were seeing in high dimensions, they just truncate in 2 dimensions for these cases. So now you have a problem. You don't have an infinite number of constraints, but now your constraints are finite. So you can solve this problem. Now you can solve it by hand. Well, some people solve some of them by hand. These models include a lot of integrable models, or well, at criticality, right? At criticality, like the Ising model into the sine Gordon, sine hyperbolic Potts model. This is solid on solid models, ON models, and many more. However, my time is up. There is still lot of theories that are not considered in this situation, which is theories that we call non-minimal or non-rational. And that's where the conformal bootstrap can start giving us information. We can use this conformal bootstrap to start proving these other theories in 2 dimensions that are not contained by minimal models. And that's something that I am thinking about and working on. It's beautiful because we have a lot of elliptic geometry that just pop up out of nowhere. So it's kind of mysterious, and you have some results that actually, my clock is up. And you have some, actually there are some relation of those interesting functions with supersymmetric conformal field theories in higher dimensions, which is kind of mind-blowing to me. But that's pretty much it. So thank you for your time.
Thank you, Carlos, for this nice talk. So there is time for questions.